Running an extended conversation with a modern language model requires immense physical hardware. A few days ago, researchers at Google published a paper detailing a potential solution to this requirement. It is called TurboQuant. This diagram illustrates the research paper's headline metric, shrinking a large language model's active memory footprint down to roughly 20% of its original volume. It achieves this compression by reducing standard vector precision from 16 bits down to just 3.5 bits. The tech community immediately reacted to the publication of this paper. Specifically, a widespread claim emerged asserting that this five-fold memory reduction finally enables local, on-device deployment of flagship language models for smartphones. This conclusion relies on flawed engineering logic. TurboQuant is a highly effective breakthrough for server-side scaling, but it does not address the other fixed hardware constraints required to run a model locally. To understand why, we have to deconstruct how this memory compression actually works and identify the hardware barriers that prevent mobile deployment. Optimizing an AI's active data processing is meaningless if the physical device lacks the foundational baseline hardware to hold the model in the first place. To maintain context in a long interaction, a language model must hold every previous message of a conversation in its active memory. The technical term for this active memory is the KV cache, or key value cache. This diagram shows the foundational data conversion step. Every word you type is converted into a distinct block of numerical data, known as a vector. Standard models require 16 bits of memory to store just one of these numbers. Now, consider the scale of an average interaction when a conversation reaches 30 messages deep. Those 16 bits are multiplied across thousands of individual numbers for every single message sent and received. This dynamic memory accumulation grows linearly with every new prompt you input. Physically, the model's active memory expands until it monopolizes the server's RAM. As the hardware struggles to juggle this expanding data, the user experiences slower response times and sluggish inference. Without a method to compress the KV cache, infinitely long AI conversations remain physically and financially impossible. Google's TurboQuant algorithm provides a specific mathematical solution to the KV cache bottleneck. This diagram illustrates the intervention point. TurboQuant specifically targets the 16-bit vector blocks inside the active memory. The algorithm applies a compression method that squashes each number down to just 3.5 bits. This produces a five-fold reduction in the total active memory required to keep the exact same 30-message conversation alive. Dropping nearly 80% of the data precision presents an obvious engineering concern. It should destroy the AI's contextual understanding. The solution to this precision loss is found in the readback phase of the TurboQuant architecture. As illustrated here, when the model needs to recall earlier messages, it reads the highly compressed 3.5-bit data alongside a standard 16-bit control stream. The resulting output stream from the 3.5-bit data is near identical to the original 16-bit baseline. This proves the model retains full conversational awareness despite the massive reduction in data. By successfully decoupling conversation length from linear memory cost, TurboQuant solves one of the most expensive problems in AI inference. Looking at this schematic of a smartphone's internals, we can return to the viral claim that this five-fold memory compression makes mobile AI deployment possible. This diagram outlines the absolute reality of edge deployment. Running an LLM locally requires satisfying three distinct, rigid hardware pillars. The first pillar consists of the static weights. These weights dictate the model's core intelligence, requiring massive, fixed amounts of RAM just to be loaded onto a device. The second pillar is the compute chip. The local processor must possess the speed to execute billions of mathematical operations per second. The third pillar is the dynamic KV cache, the active conversation memory we just deconstructed. When we apply the TurboQuant reality check to these three pillars, the bottleneck becomes obvious. TurboQuant optimizes the KV cache, but it does not account for the physical footprint required for the static weights or the compute chip. A smartphone simply does not possess the baseline RAM required to hold a flagship model static weights, regardless of how small the active memory gets. Conflating the compression of dynamic active memory with the compression of static foundational memory is the root cause of the edge deployment fallacy. This breakthrough belongs in the hyperscale server farm. TurboQuant was engineered for industrial server architecture, not consumer electronics. Implementing a 5 times smaller KV cache at the server level produces 3 measurable, real-world consequences. As detailed in this diagram, the first consequence is exponentially longer user conversations without system degradation. The second is significantly faster token response times. The third is a drastic reduction in physical server costs. Shrinking the active memory footprint allows AI companies to serve 5 times as many users on the exact same physical hardware. This alters the unit economics of running large language models at scale. Progress in AI architecture requires precise definitions. Optimizing cache is a significant feat, but it is entirely distinct from optimizing model weights. TurboQuant will not put a flagship language model in your pocket today. But it is the type of invisible, back-end engineering required to ensure these systems do not collapse under their own compute costs tomorrow.